100 invited talk. He currently serves as a principal editor of JMR. He is a fellow of Materials Research Society and fellow of Microscopy Society of America. Please welcome Dr. Wang.
Yes, thank you. Thank you, Professor Kim, for the introduction. And let me see if I share my screen. And is this properly in the presentation mode?
It's not full screen.
Not a full screen? Okay, let me see. Swoop. No, it's fine.
Okay, now it's fine. Thank you.
Okay, thank you. Yes, thank you, Professor Kim, and the organizer for the invitation. It's really a great pleasure to give a presentation and discuss what's going on the battery, on the case of the anode and their materials. And I already use electron microscopy as a tool for diagnosing the battery. As you can see from my title, and from this, what kind of diagnosis, and we can capture some insight and to see how this can be used to get the design of new materials for the batteries. So first of all, just to mention where we are. And this is a map from Washington State, and from Google, you can see the Washington State is corner. And magnify this map, you can see we are in Richland, and Seattle in here, Portland in here is a triangle. We are in the desert area in this position. So in the research philosophy, and I really closely see several things come together: processing of fabrication of materials, and characterization, and theory and modeling, and the property performance. And this really the four corners, it's really supports materials applications, and the similar for batteries as well. So really comes the battery research, and in our laboratory, we have a range of materials synthesis in the center. For example, we have the characterizations with different technique, and in the materials in their applications, we have different scale of their fabrication, like a punch cell, for example, for the batteries. Here, this integration together, and really move this field forward. So talking about electron microscopy, and this really, I regard this as a frontier of electron microscopy, and aberration correction, that's one domain developed over the last 20 years, is really kind of enhance the spatial or the energy resolutions with the microscope. That's very one domain. And another one is actually nowadays with this technique, we talk about 3D, 4D, cryogenic image conditions, chemistry and their structure. That's kind of another domain here. And a lot of chemical reactions going very faster. And can we capture these kind of reactions and with very faster time? This is called ultra-fast microscope, another domain. It's really kind of mostly inaugurated by lead Professor Taiwell from Caltech. And what's my domain here is really an in situ microscope, and I will show some examples what I have done on those directions and how we can gain certain insight from here. So talking about in situ microscope, this kind of typically I show you environmental microscope and a high vacuum microscope in here. And you see, you get this kind of microscope in the commercial available, and you want to in situ something just you can commercially available in some way. You need to be inventive and think how to design experiment to do the in situ in there possible. So there are kind of domains we can play around. The knobs, for example, on the stage, for example, you can nanoscale manipulations. For example, you can heating, you can cooling, you can bathing, you can go to the liquid stage or gas, or you can get other kind of stimulus photons, for example. All this on the stage you can play around. Within the microscope domain, you put different detectors, for example, for EDX use or other kind of spatial and temporal resolution methods as well. That's kind of on the microscope domains. On their nowadays machine learning and their computer sensing, for example, you really can use this kind of data processing technique and help you to accelerate what you're doing here. So indeed, we have a range of knobs in here, and we can play around and to do what we are trying to solve the science question. So I put in here, I summarize and really what you're really developing in the laboratory. For example, open cell in situ for battery research. That's we done substantial work along those directions. And closed liquid cell, for example, for battery research. And we have an environmental microscope, and you can leak a gas around the sample. You really kind of make different gas, for example. As Dr. Lu just mentioned about lithium air, and we can do the lithium air battery as well in here. And definitely, I think Professor Yi and Shirley actually inaugurated the use of the cryogenic microscope for battery research as another domain directions. At the same time, we integrate different techniques. For example, we integrate force measurement into the microscope, environmental or other microscope, and really can measure small forces in here. I will show examples along these directions. And at the same time, we integrate other techniques as well. For example, liquid assays, for example, second ion mass spectrometer is another technique, and we can integrate with microscope as well, and to do in situ TM studies and combine together to solve the problem. So talking about battery, I think within the community, I think people know this very well, with different applications into the grid and mobile applications that's critical for energy storage. And to give a general idea how much energy nowadays we need for our routine use, for example, from cell phones and from the cars, for example, and all this kind of thing. And what we need to really strengthen is energy density, for example. We want more energy packed in the device. And the cost is another very, very important factor. And the safety, and how long cycle life, and how fast you can charge when you use up your battery. And the resources is very important. And cobalt, nickel, for example, is becoming more and more expensive. That's a challenge as well. And we need to be inventive and find other earth-abundant materials and for the batteries. So if you come to the battery, and we know the concept very well, you get a cathode, anode, electrolyte, and you get ion shuffling between the anode and the cathode, and electrons going outside help us to work, drive the device. And let's look at sample. While we face a lot of challenges here, with each charge and discharge, and the anode, cathode, electrolyte, and the interface just evolve gradually a little bit. And with continuous extensive charge and discharge, each of these materials, they become gradually fading away. So that's a kind of how we know what's going on here, and we solve the problem. That's kind of our diagnosis tasks. So you look into battery materials, and there are so many cathode or anode potentially. In the bottom, typically it's kind of anode materials. On the top is possibly mostly cathode materials, and then you combine them together. This really gives us a lot of concepts in the battery: lithium battery, metal batteries, lithium sulfur, air, lithium carbon dioxide, or redox flow batteries. All these concepts really depend on different materials combinations. So with this one, I think I will show three examples today with a time limit in here. So first, I think I show about silicon. And silicon, I think we study a long time, I think about 15, 20 years, I think. It's kind of, I try to see what's the fundamental understanding about silicon. And the challenge we are still facing, and then we get into the insights we have gained, and towards what we can design a better silicon for the applications. And this, I think, I put this picture again, and chart again here. And the silicon, you can see very high capacity. But if you simply take a silicon, make a battery, you know what will happen, and it's fading away quickly in some way. So I show this movie, I think I love this movie, and this is in cooperation with Professor Yi from Stanford. And you get the silicon particles in here, small or large, and they're collected together. If you try to inject silicon and lithium into silicon, that's what you see what happens. The smaller ones, they just maintain a cold shell decision process, while larger ones, because of stress generation, they just explode because stress, they cannot sustain that one. So based on this movie and a summary in here, what we learn, and it seems we choose very critical dimension. With a particle smaller, you will not fracture, and you can use nanoparticles to make a battery. That's possible one implication for the community. And I put in here and show exactly what happens. People say, okay, there are critical dimensions. Silicon, if you're larger than 100 nanometers, and then you get the fracture. So we do not use silicon to this dimension, and they use smaller ones. Okay, let's sound their simple, use smaller ones, and you list it with coshell structure, DLSH, and one thing you can see, regardless how large the silicon particle in here, or regardless how long you release it, and then you always maintain a small core in here. This is because stress fracture, and the more you release it and the more stress in here, and then thermodynamically you can no longer make this whole particle fully listed. That's principle that I think is well understood. So one thing that when silicon listed, you get about 300% volume expansion. Now in the liquid cell, and then you form this kind of SEL layer on the silicon particle. So the community, I think, really focused a lot of efforts, and a lot of I think is kind of imaginations. And you get your silicon particle in here, you get the liquid electrolyte, and then you go through lithium, and then you form SEL layer, subsequent one state in some way. So now there are several scenarios is possible. One is that SEL layer becomes stretched if you continue to list the silicon because silicon continuously expand. Or another way, you silicon continuously expand, and the SEL layer becomes thicker and thicker, and they maintain integral in some way actually. So another way I think they just get a simple fracture in some way. That's another scenario. If you take lithium out, silicon will be shrink back. There are different scenarios in here. One, the silicon simply go back and they form kind of hollow structure in some way. So another way, silicon and the SELA gesture, is bounded very well with your silicon, and the gesture crumble and they stick with silicon, and the gesture crumble together in some way. So another way, I think you can imagine it's possible. You get a kind of gap in here because the weak interface in here. That's another possibility. So which is true, and there's different research going on, and they're trying to figure this out. So one thing actually, the community possible is a puzzle for some time, and this Professor Yi's result. For example, you take a silicon nanowire, and you assemble a battery, and then you charge and discharge and cycle the battery, and after certain cycles, you can see the silicon become a kind of a fluffy structure. I think the community knows this phenomenon, but we never get an answer what's going on here. So there's a silicon nanowire in here. Another thing, I think people make a different silicon nanowires and putting the silicon on the copper wire actually. And you cycle the battery, and you see the silicon become kind of fluffy as well after cycling. People never understand what's going on here. This is a kind of puzzle. And take another particles of silicon, the similar thing going on here. You see initially it's kind of dense particles in here, and you cycle once, and there are 5 cycles, 20, 40, 60 cycles, and gradually similar thing happens as what we saw in there. It becomes fluffy or porous structure or something. So what's really going on here? And I think is a little bit puzzle. So to solve this one, I show you here again, actually, if silicon, and you put the lithium in silicon without a liquid in there, and you can see it's kind of expansion and shrink, there's no problem. But you put the liquid electrolyte, and you cycle the silicon, and it become fluffy structure or something. So what's really going on here? And we really kind of try to solve this problem, and we really grow silicon nanowire on the kind of nickel plate in here, and we make a cell configuration, and with cryogenic microscope do the use and their tomograph imaging, really from the beginning, and to cycle gradually different cycles to monitor in the structure and chemistry what's going on about silicon. That's what I show you what we have done. So this is fundamentally, this cone cell with a nanowire in here, and then you cycle the batteries. There's a voltage profile. and you cycles, you can see the capacity gradually decreasing. And then we monitor the structure very carefully. So this is a stem image, and there you can see after first elicitation, you can see, okay, this unreacted silicon here, and there it's kind of this is the silicon here, and there you get SEA layer on the very top surface. So the first cycle, and then after 36 cycles, you can see you get a little bit of porous structure in here, and the SEA layer becomes thicker in some way, and that's really what's going on here. So we continue to cycle the battery with different cycles and to see what's going on here. So that's what's really what we can see. The first cycles you can see is look kind of this is the silicon's integral structure, and after 36 cycles, and there you can see the gesture become a kind of porous structure, and you get a core in the center as well. And then after 100 cycles, they really wasn't sure, probably E3 and other groups show similar things. They become a kind of different shape and also become porous structure or something. So what's going on here? And there, with 3D elemental mapping, and there this kind of tomograph, in 3D actually we build up and to see how the structure looks like. Once first cycle, so the 6 cycles, and there are 100 cycles, and there you can see that's kind of tomograph reconstruction to show what's going on here. So if you map the elemental distributions, you can see fluorine and oxygen is typical elements from the electrolytes. So this can be used as a signature element, mapping the SEA layer in here. So we make in the first cycle in here, for example, you really form a core shell structure in here. You can see you put a silicon fluorine, and there you form a core shell structure. And then after 6 cycles, you can see they become much thicker SEA layer and the silicon and the SEA layer mixing together in some way. And then after 100 cycles, you can see silicon and the SEA layer component, we just form a kind of a composite structure in here. So this really indicates the fluffy structure. This indicates SEA layer like going into the silicon. They just not kind of like people just we imagine from a kind of like a first cycle from a core shell structure or something. They're not maintaining the core shell structure. Instead, the SEA layer gradually get into silicon. That's what you're based on this kind of tomography and elemental mapping, what we found in here. That's kind of reconstruction I show you for first cycle, and there are 36 cycles, and you can see that the different that's morphological and the chemical compositions, silicon. And after 100 cycles, that's different. They can become kind of severe kind of damage, and there you can see the different elements and their morphological evolution as well. So this really indicates silicon in the liquid electrolyte. When you cycle that one, they're not simply just a kind of SEA layer and the silicon the core shell structure. Instead, the SEA layer gradually cooling into the silicon, and there. So how does this happen in here? So what we did is use kind of Freezefilled modeling, and there you get a silicon here. First time you release it, there's no problem, and there when you delete it, you take this lithium out, and there apparently produce a lot of weaknesses because lithium left, and then this weaknesses, how this weakens behavior is critically control the morphology. If you take lithium out very quickly, and this kind of weakness can condense and form a large void in some way, actually. That's what really happened. If you form a void, and the liquid can penetrate within this void, and then gradually at kind of a corrosion process. It's kind of in the cross-section view, and if in this direction, and you can see initially form a kind of SEA layer, the core shell structure, because you delete it, and you form a kind of void because the lithium weakens in there, condense, and this kind of liquid electrolyte just penetrates kind of void near the surface, and gradually, if we cycle, it continues going on here. So we really kind of, by this study, we really kind of understand morphologically how silicon evolve gradually. So SEA layer and the silicon, they are not a core shell structure at all. They are just invading into the silicon inside, and that's morphological. And chemically, we need to understand what's going on here. So in here in the middle, I show you what's going on here. We use the yields actually capture what's about the silicon bonding or electronic structures actually. So in here is the first cycle we capture yields from the surface. You can see silicon like this, and the silicon in the core of the particle like this. And then if you start the 6 cycles near the surface, it becomes this now, a lot of silicon here, give this signature. And in the core, it's still like this feature, like in here as well. If you continue the cycling, 100 cycles, and then you can see near the core, and they're gradually more or less something like this kind of features. That's a silicon edge, actually, air edge. And then near the surface, and then in here. So with this one, and we check into the literature and about the silicon air edge. For example, this is a silicon air edge. It's a silicon. So typically, and the silicon dioxide as well, you can see this kind of feature. And the silicon and the silicon dioxide interface, you see compare a little bit different here, different peak intensities in here. So compare this kind of signature features for use, and we understand now initially, indeed, this is silicon. You can see silicon core and this silicon. And near the SEL layer, there are no silicon in the SEL layer at all. You can see it's kind of no silicon signals. After 36 cycles, you can see in the core of the nanowire is still a silicon feature in here. But near the surface, it becomes kind of more or less a combined silicon and oxygen combined in some way, more or less like this one or something like this one, silicon dioxide in certain fraction. If you cycle 100 cycles, you can see now, and they're in the center of the nanowire, and there is almost become silicon dioxide or silicon oxide as well in here. And near the surface, you can see it's much, much similar and the silicon dioxide. So this really kind of indicates with the morphological evolutions at the same time, you can see the chemical evolution with the silicon and the oxygen combined with gradually with the silicon in here, and the silicon becomes silicon oxide in some way. So some people ask her how the listed silicon looks like. So we take a silicon nanowire, pump lithium in there. That's kind of listed silicon in here. You can see we captured the listed silicon. You can see the silicon air edge in the use looks much similar at the silicon edge in here as well. So what we observe, we have very solid silicon is gradually oxidized. So what does it mean here? And this is what we captured based on what your use, and there was a model materials in here. And apparently silicon and SEL layer is not the core structure, gradually form kind of composite structure which extend the cycling. At the same time, chemically, and the silicon oxide within this electrolyte, EC-DMC with 3 to 7, and there's 10% of FEC, additive in here. So we really solve this problem and get some insight from here. So what's the indication? And I collect this one for some time, and you look into the people use different concepts to design this kind of silicon. And for one way or another, I think this kind of coating or confinement effect is really trying to separate the liquid electrolyte from silicon. That's the right direction, I think. So I think based on what we captured here, a proper way to do that one, I think we really need to I think your share from this concept is very smart idea. You really need to isolate the silicon from a liquid, and the York shell structure. That's one way to do that one. And another way, I think Professor Chongmin Wang from Maryland is I like this idea very much, and it's really kind of you really can design the SEL layer with lithium fluoride rich composition in there. At the same time, it's very potent, and makes the interface very much weaker. And instead of when the SEL layer is easy to form, and then it just like a hard shell, and then the silicon inside just keeping shrink and their expansion when you try to discharge. And that's really kind of I think what we observed and really consistent with two concepts, and that's really I think it's make a silicon work. So that's really kind of my first talk about silicon and what we have captured within the community, and what's a right path and for going forward. And so next one, I think talk a little about the lithium dendrite growth, and we're trying to answer the questions: how strong is the growing lithium dendrite? And that's kind of mystery for some time, and what kind of cause? What's the intrinsic cause for controlling lithium deposition morphology? And you get different morphological particles or whiskers, and what's the intrinsic code for that one. And then we from here, and we can capture, we can to see what kind of possible paths for controlling lithium depositions. So you look into the dendrite, and there is not something new, and there are different metallurgical materials, or the snowflakes in the dendritic morphologies, and there, in our IC industry, and there in this kind of thin whiskers is another problem for the circuit industry. They always grew this kind of thing, and make a short circuit in here. And for lithium dendrite, it's similar things. And you grew this kind of dendrite, and people think this is strong enough, puncture the separator, or the whisk or something, or make a fracture of the separator, and then make the short circuit. Is this true or not? That's kind of, is people's speculations. And we can imagine, the grass, for example, or the weeds on the road, on the pavement. They're very weak, actually. And then if they build enough stress, they can really, fracture or this kind of asphalt pavement in here. So lithium dendrite possibly behave similar things, and so it's very necessary to measure how strong a growing lithium dendrite will be. And I just mentioned that we have an environmental microscopy here, and this is a sample, and you can leak a gas around your sample, and so oxygen, nitrogen, carbon dioxide, or water vapor, and you can leak around a sample with a computer controlled this kind of smart gas delivery system in there. We can do that. What we found actually, if you leak carbon dioxide in here, you make a heated battery in here, and you can grow lithium whisk in here. So this really offers us opportunity. We can measure how strong a growing lithium whisk in there. That's what we do in principle with the environmental microscopy here. And there we integrate AFM cantilever on the manipulator. What we're doing here, like AFM cantilever is a spring here, and you grow some lithium dendrite with a spring here, and then lithium dendrite grow and trying to grow, and then the spring trying to push back. So which is strong, and then if you grow a lithium whisk and you compression the spring, the distance, and you calibrate the spring constant, and then how much a growing lithium dendrite will apply the force on the spring. If you put the separator here, you can imagine how much the separator will sense the stress. So let's watch a cell in here we assembled in the environmental microscope, and you get the lithium metal and the lithium oxide as kind of solid state electrolyte. And this AFM cantilever, we integrate this one in the microscope column. For example, if you bias that one, and you get we get a carbon dioxide gas in here, and then this makes a lithium whisk grow as a whisk in here actually. If you put the nitrogen, we not grow like this, and I'll show some results. And this really can give us the measurement of how strong a lithium whisk can grow in there. That's really kind of TM image. You show this AFM cantilever in here. You can see it's a lithium metal in here. You can grow tandem in this direction. And the AFM cantilever will be pushed up, banded, and then we know how much stress in there by the lithium whisk in here. So the first, I think, again, I show you what's the principle, what we're doing here. When you play this movie, you can see on the top is the AFM cantilever. You can see it's an initial nucleation of lithium particle. It's a single crystal particle actually in here. And then it's just your nucleation. And above the critical set of nucleation, and it grew very quickly. And then because you push up the spring, and the spring push back, and then the lithium wick is not such strong, and they just push back, and you just get kind of a failure of the whisk in here. You can see it's just so. But this way we can capture different time, and we can capture nucleation process, and the growth actually you can see that's kind of if you do diffraction, it can initial nucleation is kind of single crystal lithium particle in here. Definitely, you can measure the time and the distance, and then you can derivatives is a speed, and it's kind of initial nucleation, and the grows very faster, and then to certain stress, too long, and then just a failure very quickly actually. So it's really offer our opportunity, and there are different ways. That's kind of whisker we do the diffractions, and there show it's really kind of single crystal metals in here. So we can monitor different growth modes, for example, because if you change the spring constant of the cantilever, you get a much stronger kind of compression, and then you can see initially too much stronger confinement, and then you get a compress kind of compression, and then it just grows in the sideways or something, and eventually they just enable to grow the thicker whisk in here. That's what's going on. You can see they are strong enough, and they just put the spring up, and their spring trying to put it back, and now the force become larger and larger until one point, and they cannot sustain the force anymore, and then just your failure by buckling, for example. That's one failure mode, and let's see another one. I think is a single crystal. It's already have certain lines, and you can see if you continue the growth, and then there's a spring, and this is strong enough, and you can see there are defects in here as well. And eventually, this whisker will be filled by kind of kink formation in a single crystal in here. That's what you will see. It continues grow, and they're now almost out of view, and we change the magnification. You can see a swapping and moving in here. Yeah, it's keep going, and they're strong enough. And now because it's out of view, and we change the magnifications, and you can see all the defects forming here is a kink actual formation in here, and the gesture eventually be filled by this position. So it's really kind of give us opportunity and study how the whisker grew and the failure. And then if too much stress in here, and again I think people know this, and they're trying to it's kind of you can see it grew a little bit, and then stress increase, and then now it's just become no longer, and then it becomes thicker and thicker. That's stress factor. So this really kind of indicates when you do the battery, and people overuse the stress, and you can regulate the lithium deposition morphology here as well. So this really gives us opportunity, and we can build up, with different spring constants, and there are different failure modes. You can get a buckling, for example. You get a lateral growth because stress, and you can grow much thicker or something. A single crystal can get kink formations. That's another failure mode. So fundamentally, different failure modes have different stress. For example, this curve really kind of you can calculate it out. Actually, it's kind of a buckling factor. And this is the yield, for example. If you get a weak kind of confinement, and the whisk can grow very fast. So this means that you can grow along this direction, and very long, and then you meet this kind of interactions, and you failure actually in this position in the buckling. Actually, if you get a weak, a stronger confinement, and then you grow slower actually some way, and then you move along this direction, and then you find it's a failure along this kind of blue lines actually. So really build up kind of failure mode for the lithium whisker, and that's what's based on our in situ studies. So as I mentioned, I show you different gas environments, and this is in the carbon dioxide, and indeed you can see the whisk morphology formation here, similar things. And we just wonder if we put it in the nitrogen, and what's going on here. So you can see that's in the nitrogen, and we never see kind of a whisker growth in the nitrogen environment. So this means in the ICA layer in here is lithium carbonate. They grow the whisk in here, but with nitrogen gas, you get the lithium nitrate, and then you never grow a kind of whisk morphology. You always grow this kind of particle or something. This really indicates ICA layer play a big role for the whisk morphology in here. So with that one in our mind, and we design a kind of use a coin cell, and demonstrate our kind of hypothesis. We use a kind of base electrolyte, and in this electrolyte, and you get kind of lithium particle growth in here. So because the lithium carbonate is a key component for the whisker formation, so we point this kind of base electrolyte with 0.2% of EC in here. And then with 0.2% EC addition, you can see the forming certain fraction of the whisker in here. And then we further increase the EC concentration to 2%. And then you can see compare with the base electrolyte, and now with only 2% of additive here, and you get a lot of whisker formation here. So it's really consistent with what we captured based on the in situ TM studies. Lithium carbonate play a bigger role for the lithium whisker formation, and they really kind of in console, we demonstrate these principles in here as well. So with that, I already summarized about lithium dynamic growth, and there is really kind of lithium morphology really controlled by SEL layer. It's really kind of follow classical, crystal growth model and the interface properties between the SEL layer and the lithium, and play a big role for the morphology. And you change the interfacial energies, and then you control the morphology. Apparently, lithium whisk is not strong enough to puncture possible some solid separator or something. Well, I think a recent work clearly shows that when it's a kind of a stress corrosion model, like what the weeds or something underneath the pavement, gradually build up stress, make the same fracture. That's really kind of one insight that we capture here. Based on my understanding, I think more work needs to be done actually about the SEL layer properties, and there's kind of a lot of work needs to be done along this direction. I think that's kind of what we can capture from the in situ, and there about more work to be needed to be done. So the last thing I think I'll talk a little bit about the layered structure KAIST. Intragranular and intergranular cracking is a very common phenomenon. This I think a lot of understanding, and there are a lot of challenging questions still remain there. And what's the intrinsic cause for the cracking behavior? And the community seems called it cracking. I think there's some kind of puzzling thing still going on there. I think we illustrate what's really going on there. So with the layered structure KAIST, and they're dating back about 10 years or something, and they're or a little bit earlier, and the people use kind of small particles as the KAIST particles, and to increase this kind of packing density, and people begin to make this kind of granular structured second particles as a typical example in here. You can see so one key question that when for this kind of single crystal particles, and the primary particle within the second particle, are they behavior similar, or what's the difference here? So based on our study, and we see that each primary particle, their behavior is the same as what we see in here, the single crystal particles in here. So these are collective behavior, and then definitely we get the kind of intergranular cracking, and I will show examples here. So typically, this kind of is lithium, nickel, manganese, and cobalt, and MC, this kind of particles, second particles in here. It's a pristine electrode without cycling. You can see make a cross section, and apparently you can see it's very, very clean in some way actually, and there no cracking or something. And after you cycle that one, and then you can see it's kind of you get this kind of like a cracking or something. So people call it cracking, and they regard this as a mechanical effect. But I think I will show you I'm very preserved or reserved about this point. It's just a mechanical effect. Let's show examples of what's going on here. It's definitely a thinker. So one level I show you this kind of intergranular current is cracking between the primary particles in here. Another level of cracking or somewhere you can see in here with the STEM imaging clearly show what's going on here. This is kind of if you go to a relatively low voltage 4.2, and then you can see a smaller kind of cracking, intergranular cracking. And there are no intragranular cracking. This means that cracking within the grain actually. If you go to 4.5, and then you can see the gap between the primary particles a little bit larger. At the same time, and there you don't see any kind of intragranular cracking at all. If you go to the 4.7 volts, and then you can see apparently the separation between the particles become larger compared with the low voltage, relatively low voltage in here. At the same time, you can see this kind of dark contrast in here, and we call this intragranular cracking. So what's the nature of this kind of stuff? And I show you here again. And apparently this kind of intragranular cracking, and in the STEM imaging, it really looks like cracking here. And that's our own publication, and we call this intragranular cracking. And you can see from here, this image shows this kind of stem imaging, and it looks kind of transition metal very brighter, and it gets very dark, and here kind of binding the wall. It looks like a cracking going on here. And our recent study actually, this is not really kind of cracking. There are some materials within this one. If you're really cracking, it's two materials separation in some way because they kind of fracture. That's kind of with certain resolutions. That's one thing. And we definitely can measure this kind of so-called cracking density, and with the voltage, actually, you can see as a lower voltage, and there you get your lower density, and you get a higher voltage, and then you get your this kind of cracking density increase of the wall. That's kind of apparently correlated with what you're going on with the voltage in here. And the true nature of this kind of stuff, I think I will mention this again in my summary. What's going on here? So I show you three very good examples, and we talk about the intragranular cracking and between the primary particles, and this work really come from PNNL and Jesse Zhang's group, and this really come from the Hong Kong and Argonne group, and this come from South Korea and the MIT group, and what kind of these three work, and what had been done here is they put kind of different solid electrolytes along the interface between the primary particles. And then we see the battery cycle become much stable, and a lot of signs the cracking, the intergranular cracking goes away. This is very promising for the battery. You can see with this kind of infiltration of this kind of green boundaries with the solid electrolyte, and with three different electrolytes in here, and the unanimously see, you can see the performance become much better and stable. So in microstructure, it's very interesting, and you can see in the pristine, if you do not put anything in the ground boundary, and you get this kind of so-called intergranular cracking, and you put something along the ground boundary. For example, this comes from our group, and you put the lithium phosphate in here, and then after you cycling, and then there's no cracking. If you believe this becomes pure mechanical effect, now if you take a same amount of lithium out from each primary grains, and then mechanical effect is still there, why is there no cracking here? So that's a key question we need to answer. So we use a microscope very carefully. So this kind of is a pristine, the secondary particles. You can see that's a cross section, and then we do the lower mag TM imaging, stem imaging, and you look into the particle morphological structure, and it's a layered structure, very well layered structure. If you in the grain boundary, you put nothing in there, and you cycle the battery, and now you can see the diffraction. They become diffused in some way. And you see here in the bright field TM imaging, you can see the grain gesture, kind of something going on the grain actually become kind of whitish contrast in here. I believe like it's like a kind of liquid electrolyte going into the grain boundaries in here. And if you image the primary particles in here, and then you can see the phase transition going on here within the particle. It's a layered structure. Now they become kind of like a pseudo rod stock structure, or kind of a spinel like structure or something. Now, if you put this kind of put the grain boundary with this kind of lithium phosphate, for example, block the grain boundary, liquid will not penetrate along the grain boundary. That's what's really going on. You see the diffraction as a primary one. After you cycle the battery, and it still remain very sharp. And the particle is still dense in here. So in here, you get this kind of separation of the grains. And in here, you still see like a primary ones. And you check into the particle, and on the surface, you still really maintain the layered structure. So this indicates if you block the grain boundaries, and then the liquid is not getting into here, and then this kind of phase transitions, and the dissolution will not going on here. So I really think it's not this kind of we call it cracking, the pure mechanical effect. It really come from the dissolution process. Play a bigger role, I think. So with that, I think this kind of we try to model with Professor Zhang from Penn State. With each grain, you take lithium out, and then each grain, the deformation is certain, and then we try to see how much stress in here. We can understand how much the stress will contribute to this kind of so-called cracking, at the same time, how much it come from the dissolution process. So lastly, I think I summarize about this cathode materials, and this is my colleague Jie Xiao's group recently observed, I think, for the layer structure, when the battery is in the cycle, you can see the layer structure and the gesture gliding in the layer, actually. So this kind of thing is predicted by San Diego group. And then the key question, how a layer gesture can gliding here. Classically, in the metals, you can see that the metals can gliding through the dislocation model in here. But how a layer structure can be just gliding in here? That's one key question, I think. We need a little bit more understanding. At the same time, the gliding, and as I mentioned again, it's kind of a so-called integral cracking, the nature of the cracking, and how this formed actually. I don't believe it can pure mechanical fracture. There's something going on here. We don't understand nature, and we don't understand the origin of this kind of cracking here. So with that, I already summarized, and I show you kind of with the microscope, you really can diagnose into the battery materials, and we gain certain insight in there. This can be used to get us design new materials, and a lot of things looks very obvious, but I don't think we really understand that one. At the same time, I think a whole large group of collaborators within the PNNL and outside the PNNL as well. I really thanks them to working with me, and I really come from DOE, and the DOE give us the support from ERE and their BS in the materials. So thank you. I think my time is up. I think I'll stop it here. I'm happy to take some questions.
Thank you very much for the beautiful presentation. We have the 4 questions, but due to limited time, then I will introduce the 2 questions. The first question is thank you for a great talk. The environmental TM with the AFM tip is a fascinating characterization approach. I imagine the dendrite would feel increasing compressive pressure as the dendrite grows, pushes against the AFM tip. Is this an issue that should be considered, or is this negligible? Thank you for your insight.
Yes, that's a good question, actually. So we gesture because we try to measure how much the force of a growing dendrite can apply on separator. So we use AFM kind of cantilever intentionally to measure the stress. Yes. Yeah, I think it's not an issue, but it's kind of a way we measure the use as a spring and measure the stress actually.
Okay, thank you. And next question is, thanks for the wonderful lecture. I wonder how the dendrite nucleation would be occurred within oxygen atmosphere, which correspond to the lithium oxygen battery.
Yes, in here we use in the lithium oxygen, and we see, I think as Dr. Jun just mentioned, we see kind of different phase formation if you use oxygen, and we only find that in the carbon dioxide you can form this kind of dendritic or viscous morphology lithium, and oxygen is form different phase of lithium superoxide and peroxide, for example. They are not from dendrite at all. They form kind of like a bubble or something. That's what we study as well.
Okay, so thanks for your kind explanation. Then I would like to thank Dr. Chongmin Wang again.
Thank you, President Kim. Thank you.
Thank you.